What happens when a vision model has to read a blurry street sign from 3 blocks away, and there's a coffee shop sign right next to it with the exact same color scheme? Most multimodal models today would guess the coffee shop sign every time, because they can't zoom in on the part that actually matters. This week in vision research, we're watching models learn to look instead of just see. And the results are honestly kind of wild. Welcome to AI Frontier Weekly. Every Sunday, I break down the week's most consequential AI research so you know what actually matters. Let's dive into what happened in vision and multimodal systems for week 22. Here's the dirty secret about today's vision language models: they're incredible at recognizing a cat on a couch, but put a complex technical diagram in front of them, or a high-resolution satellite image, and they start hallucinating details faster than a sleep-deprived intern. The core problem is simple: when you feed a high-res image into a multimodal LLM, the number of visual tokens explodes. More tokens means more computation, which means either you downsample the image and lose detail, or you blow past your GPU budget. It's a coverage versus efficiency dilemma that's been quietly throttling the whole field. 2 papers this week took very different runs at the same problem, and one of them is almost elegant enough to make you jealous you didn't think of it first. CVSearch introduces a training-free scheduling system that asks a simple question before burning compute: can this image be handled by a fast expert model? If yes, done, you're out. If the expert fails, it's low confidence or ambiguous, then and only then do you escalate to semantic-guided adaptive patching, which surgically slices the image into only the regions that need higher resolution. The result? State-of-the-art on high-resolution benchmarks, 0 additional training. It's like having a senior radiologist do triage instead of reading every single X-ray yourself. On the completely opposite end of the spectrum, GASP asks, what if spatial reasoning doesn't need language supervision at all? Most 3D reasoning today is trained on VQA data, question-answer pairs about spatial relationships. But Chun-Xiao Ye at the University of Michigan showed you can get spatial understanding to emerge purely from geometric priors. They added a small correspondence head as deep supervision, trained on point correspondences and depth consistency, and the model's internal correspondence rate went from under 5% to over 70%. Benchmarks jumped 18% on all angles and 29% on VSI bench, and this used absolutely 0 3D VQA training data. That's not an incremental improvement. That's a fundamentally different approach to how models understand physical space. You can't train great vision models without great data, and for years the bottleneck has been scale. Not just any scale, permissive scale. Open datasets exist, but commercial use restrictions have kept them out of real-world products. Academic datasets are often small or locked behind institutional agreements. Then this week, the Stanford Vision Lab dropped GPIC, 28 trillion pixels across 100 million images, all permissively licensed for both research and commercial use. Let that number sink in. 28 trillion pixels is roughly the equivalent of every photo uploaded to a major social platform over several years. This isn't a dataset you curate, it's a corpus that redefines what curation even means at this scale. The paper describes the infrastructure required to even process this thing, and it's a fascinating look at the engineering behind data at planetary scale. For anyone building a vision model right now, whether you're at a startup, a university lab, or inside a large company, this is probably the single most practically important thing that happened this week. The data wall that's been blocking progress just got kicked down. On the generation side, 2 breakthroughs worth your attention. First, VideoMLA, the first study of multi-head latent attention applied to video diffusion models. For those of you who don't speak transformer architecture, here's what matters. MLA was originally developed for text models as a way to dramatically shrink the key value cache during inference. Hidde Yeseltepe and team showed it works for video too, achieving a 92.7% reduction in KV cache, that's not a typo, while matching baseline performance on short videos and actually beating it on long horizons. Throughput went up 1.23x on B200 hardware. What this means in practice is longer, higher quality video generation on less hardware. The economics of video AI just got meaningfully better. Then there's Archon, which is doing something genuinely ambitious, unifying 7 different modalities into a single autoregressive framework for digital human generation. We're talking video generation, full-body avatars, facial expressions, gestures, voice, all in one architecture. The key innovation is a for-X token reduction for talking videos, which makes the whole thing computationally tractable. Think of it as one model that can generate a complete digital human, from visual appearance down to speech patterns, instead of stitching together half a dozen specialized components. The unification play is real, and Archon is one of the most complete attempts I've seen. Finally, ETCHR tackles a subtle but deeply frustrating problem in image editing, the entanglement between understanding an image and actually modifying it. Current vision language models are trained to both understand and generate, and those two tasks interfere during editing. ETCHR decouples them, it separates the editing pipeline from the understanding pipeline, and raises pass-at-1 accuracy by nearly 5 points on Qwen-VLA. That's the difference between close enough and actually usable for image editing applications. Looking across the week's work, the vision field